Hello everyone. Welcome to this webinar about formulas and matrix references in PTV Visum. My name is Annette Ehlert and I am part of the product management team for PTV Visum. The main focus of today's webinar is directed towards the use of formulas and matrix references, and I would like to demonstrate the functionality by showing you a variety of examples for different use cases. As an introduction, I'll briefly give you an overview of the developments over the last release versions with regard to matrices and formulas. These developments over the last years have a number of advantages that I hope to demonstrate with the examples. I will start with some simpler use cases and move on to applications with more complex formulas and matrix references, including one of the latest improvements, the table lookup. This slide sketches the developments over the last years related to formulas and matrices only. One bigger change in the past was the implementation of the matrix editor in Visum 12, followed by a number of further improvements, namely the introduction of formula attributes and formula matrices, or the introduction of the formula editor itself. Meanwhile, the formula editor can also be used in demand procedures. Today it is possible to use very complex formulas and matrix references, and also table lookup is possible. The latest improvements in Visum 15 include further functions for formulas like MSA or the calculation of the GE8 statistics. These developments are the result of your feedback and requirements to build and maintain transport models more easily. We hope that you benefit from these improvements, for example, by simplifying workflows, by improving the suitability also for big models, and also reducing the probability of mistakes. And last but not least, also the possibility to transfer parts of the model to other applications. So my objective in this webinar is to demonstrate these advantages by a number of examples. Before starting with the examples, I would like to explain what exactly we mean by matrix reference. When working with matrices, for example, creating, calculating, or changing matrices, matrices have been addressed by a number. This is shown here for matrix 13. Since Visum 14, this is not anymore mandatory. You can address matrices also by their properties. That means a combination of their attributes and attribute values. That is called matrix reference. Here this is shown for the same matrix using the attributes demand start code and mode code. The value for demand start code is HS and the value for mode code is empty. So I start with a simple example of a formula attribute. In this example, we calculate the travel time factor for links using the travel time in the loaded network and T0, the travel time in the unloaded network for links. We do that by creating a user-defined attribute. I would like to show that in an example in Visum. So this is an example from the installations, and in that case I now create a user-defined attribute. This attribute will be for links. The name of the attribute will be travel time factor, and the type is floating point number, and we will use a formula. So on this formula editor you can either type directly once you are familiar with the syntax, or you can use the buttons to the right to select different parts of a formula. In that case now I choose the travel time in the loaded network for a car divided by the travel time in the unloaded network for the same demand segment. So this is our formula. And now I will add this attribute to our link list. So you can see it is a calculated attribute. You cannot edit it. But if you change any of the input parameters, the attribute is recalculated and always up to date. For example, if I change the capacity, that has an influence on the travel time in the loaded network, and then changes consequently also the travel time factor. So we have seen that one of the advantages is that these formula attributes are always up to date. And the further advantage is that the method of calculation is documented in the formula. So the same approach can be used for matrices. In this example, we calculate a travel time factor by OD pair from the scheme matrices, travel time in the loaded network and the travel time in the unloaded network. For that, we use a formula matrix. And also this example I will show you in Visum. We change to the matrix list and create a new matrix with a number 100. We use also here travel time factor. This will be a scheme matrix, and we will use a formula. Again, once you are familiar with the syntax, you can type here directly. Or now I will choose the matrices by number. So we have the travel time factor in the loaded network divided by the scheme matrix of T0. So in our matrix list, we can see that formula here on the right. So as you can see, the values are calculated, and this is based on the matrix numbers. If for any reason you might have made a mistake and need to delete one of the matrices or change one of these, of course you get an error message because our formula matrix is not anymore calculated. If you now recalculate this scheme matrix, again you get the error that the formula matrix cannot be calculated. And now also the number of the scheme matrix has changed, and consequently our formula matrix is still not calculated. So to avoid that, we can use matrix references. So in that case, I will change here from the selection by number to the selection by property. So a scheme matrix can be addressed by the code, the matrix type, and the demand segment code. So these three attributes uniquely identify a scheme matrix. And here you can now enter the value. In this case, we will choose demand segment code K. The matrix type is scheme matrix, and the code is TTC. And now I can either do the same for the travel time in the unloaded network, or I can simply copy that matrix reference and adjust it to TT0. So this is our formula matrix defined by matrix references. So now you can see the changed formula, and you can also see that the value is now again calculated. And this calculation is independent from the matrix number. If I, for example, change the matrix number back to 60, you will still see that our formula matrix is calculated. So we have seen a formula matrix defined by matrix numbers. We have seen a formula matrix using the matrix references. And here the advantage is the matrix number is not the only meaningful key anymore. And another advantage is that formula matrices do not require memory when they are not currently accessed. So in the next example, we combine the two, meaning that we use a formula attribute as well as a formula matrix to define an accessibility measure per origin zone using our travel time factor. To do this, we multiply the travel time factor with the demand matrix, in the numerator. And for the calculation of the accessibility measure, we use then a user-defined formula attribute. So again, I will show that in our example. So first, we calculate a formula matrix. That will be the travel time factor multiplied by the demand for demand segment C. This will be a demand matrix, and again we use a formula. So our travel time factor, the matrix, we can identify using the code, which we have previously defined as TTF. We can see here in the bottom that our matrix 100 is selected. And this matrix is multiplied then by the demand matrix. And the matrix reference for a demand matrix is defined by the matrix type and the demand segment code. So the matrix type in this case is OD demand, and the demand segment code we use car. Although here you can see that one matrix is selected. So this is our formula matrix, which we have in the numerator. And next we define a user-defined attribute for zones. And that we will call travel time factor for zone Y. Again, this will be a floating point number, and we will use a formula. So now for that formula, we need the sum over all destinations from our newly calculated matrix, and the matrices can be accessed using the matrix row sum. And here we choose our formula matrix, and this is divided by the demand, also summed up over all destinations. Again, that is a direct attribute of zones for matrix row sums, and then this is matrix 55. And this is our formula for the accessibility measure. So this can now be seen in the list for zones. Again, you have a calculated attribute here. And of course, once you have calculated such an attribute, you can also display that in the network editor. For example, you can use the classified display, use our formula attribute. Now I redefine all classes using natural breaks and changing the fill style. And now I can switch on that in the network editor. And in this way, I can see our accessibility measure displayed in the network by the color of the zone. So far, our examples with formula attributes and formula matrices. So now we move on to operations with several matrices. The demand calculation with feedback loops is a common use case for that. On this slide, the workflow of such a demand calculation is shown. The calculation starts with the calculation of the initial skim matrices. That is followed by the demand calculation, meaning trip distribution and mode choice, and that is followed by an assignment. Then there is a convergence check, and if the convergence condition is not true yet, then new skim matrices are calculated based on the latest assignment. And these skim matrices are then smoothed with those from the previous iteration. So now, given that we set up such a workflow from scratch, leaving out the assignment and the demand calculation, so for smoothing the matrices, there are basically two steps involved. First, copying skim matrices after the initial calculation. In that way, we also create matrices that later contain the smooth values. And second, the smoothing itself, meaning that we calculate an average between matrices of the last and the current iteration. So that means for both operations, the calculations are similar, but for several matrices. In our case, this will be skim matrices. Although for that, I have prepared a smaller example. This is our small example from the installation. Here we calculate first an assignment, and then we calculate skim matrices. As you can see in the matrix list, there are now 4 skim matrices, 2 per demand segment. So the first thing we do now is to create a user-defined attribute for matrices. So the only purpose of that user-defined attribute is to distinguish between those 4 matrices, which are the skim matrices after the assignment, and the 4 matrices which we will create later on that contain the smoothed values. So we create a user-defined attribute for matrices. We call that smooth. This will be of type text, and the default value will be empty. So I add that now to our matrix list. So as I said, for our skim matrices, which are currently already calculated, the value will be empty. So the next thing to do is we would like to copy the initial skim matrices to create another set of matrices which later on contain the smoothed values. To do that, we use an operation of combination of matrices and vectors. And now we would like to iterate over these 4 matrices and create another matrix. The only difference for the new matrix will be that the value of smooth will be set. So to do that, we use this for loop. So we will iterate over matrices. And for the matrices over which we iterate, we use a variable name. So this M refers then to the matrix over which the iteration is currently done. So for now, I will also use the comments to explain what we can see here. So first, there's the object and the variable name. We iterate over matrices. And that part, you can restrict or define a condition that restricts the iteration to certain matrices only. In that case, we will do that because we would like only to iterate over skim matrices. That means we choose the matrix type, and for skim matrices, this must be 4. So on the next line, we have on the left side of the assignment character, here we define the target matrices, the one we create. And on the right side, there's a calculation instruction. So on the left side, we would like create 4 matrices, and each of the matrices should have the same attribute value for code, matrix type, and demand segment code. And additionally, we would like to set a value for smooth. So to do that, you can simply double-click, select an attribute of the target matrix first, and the attribute value of the target matrix should correspond to the attribute value of the matrix over which we currently iterate. That is a variable attribute. That means here we see our matrix over which we currently iterate, and from that we can pick up a value, in that case the code. And now we do that again for the matrix type. First we define the matrix type for the new matrix, and the value should correspond to the value of the matrix over which we currently iterate. As you can see, we can also simply type M here, and then I get directly to the selection of the variable attribute. So again, matrix type, and now demand segment code. Again, that must correspond to the demand segment code of the matrix over which we iterate. And finally, we also need to define the value smooth. You can also add brackets here, double click, and again, then you can select the attribute. And then in that case, we set a value which is different from empty. We use here average. So this will be our new matrices. And the calculation instruction in that case is quite simple because we would simply copy the value over which we iterate. And we can refer to that using the variable m. So this is now our first step, copying the initial skim matrices. So if I execute this procedure now, we can see in the matrix list that we have the same matrices again, with the same attributes for code, matrix type, and demand segment code, and the value for smooth is set. So if I initialize these matrices now and execute the operation again, of course the matrices will not be created again, because now we have already matrices with the matrix reference of code, matrix type, demand segment code, and smooth. So just the values are then set. That was the first step, and in the second step we do the averaging between the two different matrix sets. For that again we need an operation over several matrices. We use the combination of matrices and vectors, and again we need a for loop. We iterate now over matrices again. We can use the m as a variable name again because that variable is only used in the current operation. So in this case, we will not iterate over all skim matrices because that would mean we would iterate over 8 matrices. We will only iterate over the 4 matrices to replace the values with the average. So that means we can here use our matrix attribute smooth, and this must be average, so we iterate over the matrices which then contain the averaged values. You can also add further conditions that you can do by using the AND character. So now in our second line here, on the left side, there are the target matrices. That is quite simple in this case because that is M, or corresponds to M, because we iterate over the matrices and the matrix values of these matrices are replaced. M is also involved in the averaging, so we choose M multiplied by a weight, 0.2 for example, and this must be now added, or the other part is added from the skim matrices, which are then after the assignment recalculated. So here we use a matrix reference, and again here we need the 3 attributes of code that the value must correspond again to M code, and the same we need to do for the matrix type that corresponds again to the matrix type of the matrix over which we iterate, and the demand segment code as an attribute of the target matrix, which must correspond again to the demand segment code of M. So with this matrix reference, we would like to refer to these matrices, means we also need to add the smooth value, or the value of the attribute smooth, which in that case corresponds to empty. So with this matrix reference, we refer to these 4 skim matrices, and M refers to these matrices over which we iterate. This needs also a factor, so I will not use 0.8 in this case, I will use 0.3, simply that we can see that the values are changing. So if I execute this operation now, I can see that the values are now changed, and these 4 matrices now contain the averaged values. So that was the second operation, averaging the values of 2 sets of matrices. So that is also a good point to highlight again the editing option in the formula editor. You can double-click on any of these parts of the matrix reference, for example, one just brackets, you get to the attributes of the matrix. If there is an M in front, you get to the attribute of the matrices over which we currently iterate. That you can see here, this M refers to the attribute which we have entered for the for loop. And you can also double-click on matrix, for example. If you define a matrix, you can double-click, get to this dialog, and here you can either type or create attributes and define their values in this dialog. So going back to our presentation, we have seen in this example that in the first step we have copied the scheme matrices. We have created new matrices, and these matrices later on contain the smoothed values. We have defined a user-defined attribute smooth just to distinguish between the 2 sets of matrices. We have also seen in that example that we have done a single procedure of combination of matrices and vectors to copy several scheme matrices. Here again you can see the formula again. And also in the second step we have used a single procedure of combination of matrices and vectors and have smoothed all scheme matrices. Again, here you can see the formula. So this once more highlights the editing option in the formula editor. As I said, you can double-click on any of these parts, matrix, the variable, or an attribute of the matrix directly, and you get to the corresponding dialog for the selection. So we have also seen that the matrix number is not required anymore as a key. Instead, the allocation of corresponding matrices is done via the matrix reference. That means attributes and attribute values. And the combination of these attributes and attribute values can uniquely define a set of matrices or a single matrix. We have also seen that we have only used a single procedure to do the operation on several matrices. This consequently can result in shorter procedure sequences because you need less operation for several matrices. And we have also seen that this procedure is completely independent from the actually used scheme matrices. That means if you leave out one of the scheme matrices or add another one, you can still execute this procedure without the need to change it. So far, this example. We now continue with demand procedures. In demand procedures like distribution or mode choice, utilities are defined using scheme matrices and coefficients by demand starter, for example. The general formula for this is shown on the slide. So now I will show you that in Visum, and first I will show you how the utility definition looked like without matrix references. So I go back to our first example. I load a procedure sequence without matrix references. And you can already see this procedure sequence was longer. So if we now go to the mode choice, we can see here the utility definitions for mode choice without using matrix references. There are certain disadvantages. First of all, it is difficult to read these utility functions. There is no direct connection of the coefficients to an object of the demand model. Here the coefficients are directly entered. Also for these matrices, it is difficult to see which scheme matrices are actually used. And also if you were to change these values, it is error prone because you can easily make a mistake if you need to change several of these coefficients. So now I will show you the same procedure sequence with matrix references. Again, we go to the tour-based utility functions of the mode choice. The definitions are longer, but in these definitions you can see that the matrix references give a clearer indication which matrices are used, because here you see the attributes, demand segment code, and also the code of the matrix. Coefficients, like here, are not entered directly. They are defined as, in this case, person group attributes and can be accessed in these formulas. The advantage is better overview and a clearer documentation where the coefficients belong to. Another advantage is that the utility definition is similar for each mode. So you can easily copy these utility definitions, at least in this case, by mode. So now I would like to demonstrate to you how to replace such coefficients. Like here for walk, we still have a conversion factor. If you were to replace this conversion factor with the user-defined attribute, you can do that, or we will do that now. We define user-defined attribute for modes. We call that conversion factor. That will be a floating point number, and we use the default value of 1. If I now go to the list, I can see this conversion factor, and now I can, for example, enter a value for walk. And now I would like to use this coefficient or conversion factor in our mode matrices or utility functions for mode. So in that case, I will remove these conversion factors. So, and now I can go to variable attribute, and here this context refers to the person group or modes of the calculations for which this row is defined. So in that case, I go to mode, which is a direct relation from the matrix to mode. Here I find our conversion factor, and now I can see here the context. This context for mode refers to the mode in this row, and this context for person group again refers to that person group for which the utility definition is done here. So, and now, as I said before, you can easily copy these utility functions to other rows for the same mode because they are exactly the same. So we can also have a look at the coefficients defined at the person group. Again, they are now defined as user-defined attributes of person groups, and it is much more easy to copy-paste or get the coefficients from external sources, and it's much more unlikely that you make mistakes here rather than entering the values directly in the utility definition. So, going back to the slides, we have seen that there are certain advantages using matrix references. You have meaningful references to coefficients and to matrices. And again, because you have similar utility functions for one mode, you can copy and paste these definitions easily. Again, coefficients are not anymore entered directly. They are defined as the demand object to which they belong. So this options of defining coefficients at the demand object has another advantage. It has also benefits for the scenario management because the changes can be defined in modifications. So I will now save that version file and create a project of scenario management. to show you that we can have modifications where we can use these coefficients directly. So I use a project name, example, create a project. So the version we have currently loaded will serve as a base version in that project. So I can easily define one scenario from the base version. And in the base version, as we have seen, the procedure sequence is already defined. So I could calculate this scenario. If I were to test with different coefficients, I can simply define a modification. And for example, I can change the coefficients of number of transfers. The change will be based on the base version. And now I can easily go to our list here. I can choose the corresponding coefficients, enter a new value. Can finish my modification. And based on that modification, I can define another scenario. Here I add the modification and the calculation is now done with different coefficients. So here you have the advantage, you can simply compare results from the demand calculation with varying coefficients. So I close this project now and load the version file again. So now we have seen the advantages in the scenario management. So the next example is using the new lookup function. The table lookup function generally provides an option of transferring values from one table of the data model to another one. To define such tables, we can use in Visum, for example, points of interest. In our example, we create such a table for mobility rates. And the mobility rates should vary by zone type. And in our model, therefore, zone type. So we need a table where we have the zone type and the mobility rates. And these data are then transferred to the corresponding zone attribute. Also that I will show you in our example. So first I need to define a POE category, which I call mobility rate. I will create a user-defined attribute for this POE category. So in this attribute, we enter the values of mobility rates. So I will call that according to our demand stratum. That will be a floating point number. And I can enter a default value. So now I can open a list, change to mobility rate and change the layout. So far we do not have any points of interest. So I now create 4 points of interest in our model, simply to have 4 entries for our mobility rates. So here I will enter the values. For example, these values. And what I would like to do now, I open a zone list. I will move that zone list next to the POE list. So in this zone list, we see now the type of the zone and the mobility rate. And what I would like to do, I would like to transfer this value to this table. And I would like to transfer it if the type number corresponds to this POE number. So this can now be done using the table lookup function. So I create a procedure, edit attribute. I set the network object type for the target attribute, that will be zones. And I would like to change the mobility rate for one of our demand stratum. And here I can now enter the table lookup. I can access the table lookup also via the For button. And here internally we need to iterate over the points of interest. We give it a variable name, and I will also add the comments. So here again, we see internally, we iterate over these points of interest. Then the condition must be defined. In our case, the condition means the number of the POE must correspond to the zone, to the type number of the zone. So here we have the number of the POE. And on the right side, you can double click and get to an attribute of zones. Zones is defined as a target network object, and we can select type number. And if this condition is true, then the value is transferred and the value is written to our user-defined attribute. So again, we iterate internally over the POEs, check the condition. If the condition is true, the value is transferred. So if I execute this procedure now, we can see that the values from this table are transferred here, and that corresponds, that is only the case if the type number corresponds to the number of the POE. So here you can see the formula again, and here the result of the execution of the procedure. Of course, you can also use formula attributes for table lookup. That is a different option. And this was our example for the lookup function. And finally, we come to our last example. That is a very simple example. Formula attributes can not only be used for calculation, you can also use them for text. And I will show that using a very simple example. I define a user-defined attribute for turns. And the new attribute should be the name. And the name will consist of the name of the from link and the name of the to link. So I will basically concatenate two strings. So the type is text. I use a formula attribute. First, I choose the from link name. And in this button, you can now see the plus sign can also be used to concatenate two strings. So here again, you can also enter any other characters. For example, this. Use the plus, and now we select the to link name. So, and I can show you this in the list of turns. So here we have our new attribute name, and as you can see, that corresponds to the from link name and the to link name, and finally gives our new name for the turn. So again, an additional advantage of formulas, you can not only use them for the calculation of values, you can also concatenate, for example, strings. So final summary, I hope I could demonstrate what options formulas and matrix references offer and how they can be used in projects. Coming back to the advantages listed at the beginning, the main benefits are that formulas and matrix references improve overview and documentation. It allows you also to reuse part of your project for the next project. So you can transfer, for example, procedure sequences more easily. We have also seen, for example, that formula matrices, formula attributes, you can save memory, which is sometimes quite important. And also mistakes can be avoided. So overall, we would think the use of formulas and matrix references can be a big win for your projects in Visum. So with that, I would like to come to the end of this webinar and would like to draw your attention to the next webinar. The next PTV Visum webinar is on February 24th about modeling park and ride. Further webinars also for other products can be found on our website, and you are invited to also register for these webinars. If you have any questions about the use of formulas and matrices or would like to share your comments, you can contact us. We will still answer questions during this webinar session or afterwards per email. I hope this webinar was of interest to you, and with this I would like to finish the webinar. Thank you very much.